Hi, I'm Tom Stone, the National Sales Manager of Industrial Markets for Thermal Care. Thermal Care has been in the process cooling business for over 50 years and serves over 50 different industries.
So there's two key parts to a pumping system, the flow requirement and the pressure. Um, when we start talking about what's going to be the required flow rate, we a lot of times start with basing that on the capacity of the system. So if it's a 10-ton chiller, we're going to say, okay, we want a single flow system, which means that's a 10-degree temperature differential. So we deliver our water to the process at 50. It picks up that heat and then comes back to the chiller. It's going to return at 60. So that's a 10-degree rise. That equates to 2.4 GPM for every ton of cooling. So a 10-ton unit would be 24 GPM. We also have double flow. There's even, triple and quadruple flow, but for our example points here, these are the two that we'll really talk about. So a double flow, we would use 2 times the amount of flow rate, so 4.8 gallons per minute per ton. That would equate to a 5-degree delta T. So we're still removing the same amount of energy, but we're just doing a higher mass flow through the system, so that mass's temperature changes less. It all equals out to the same cooling capacity though. Then when we're talking about the flow rates, we need to look at our pipe sizes, because each pipe size has a certain constraint for what we would rate as the maximum allowable flow rate. And that's based on the pressure losses associated with pushing that amount of flow through that size of pipe, but also the velocity of it, how fast it's going through there, because you can actually start to erode that pipe away if the velocities are too high. Then we need to talk about pressure. So these are the losses in the system, and what they're going to actually do is that's what's going to drive what the pump requires to be able to still push its flow through the system. And by looking at that, we'll look at the pipe lengths, the losses in the actual equipment, valves, fittings, elbows, things like that. One of the things that comes up a lot in questions while discussing, and that a lot of people don't seem to grasp the concept because it's a little foreign and you don't really think about it right away, is that vertical piping loss. Everybody thinks, I'm pumping this up, and so I'm going to be fighting gravity there, so I need to consider extra losses there. But the thing that you need to consider, though, is a lot of times when you pump up, you're actually going to end up pumping back down. So as you can see here in this graphic, those dotted yellow lines, we're going to go up there at first, but then we go over and we eventually come back down. So our vertical change is net zero. So we actually lose some going up, but we gain it back going back down. So ultimately, we really just need to consider that actual linear distance of the piping itself. So we're going to run through a couple examples here real quick, just to kind of demonstrate the process that we would go through. So we're going to say we have a 5-ton chiller, and we want to achieve a 10-degree delta T, or a single flow. So we take 5 times 2.4, and that gives us our 12 GPM. So using a reference for the maximum allowable flow through different pipe sizes, we're going to determine that we need to be at 1.25 inch pipe. If we went down to 1 inch, which is the next size, it's really only good up to about 10 GPM. So we're actually just a little beyond that. So we need to bump up to that next size. What's nice there is, because we're at the low end of that new larger pipe size, we have a very small pressure loss over per linear foot of that pipe. So now what we have is we take our pump curves, and this is a standard pump curve for a thermal care chiller. We show multiple different curves on there because we offer multiple different pump sizes, because as I'll demonstrate here on the next part of the example, is that sometimes you require one of these larger pumps to meet the demands of your system. So we know our 12 GPM flow rate. So we mark that down, so that gives us a starting point. Next, we need to talk about our pressure. The pressure requirement is based on the losses in the system to ensure that we have enough pressure to push that water through the system. So we're going to use we're going to say 100 feet of total piping. So that could be essentially 50 feet from the chiller to the process and 50 feet back from the process to the chiller. That could be 10 feet up, 30 feet over, 10 feet down. It could be a straight shot. ultimately, we're kind of doing a back of the envelope calculation here to make sure that we're, in the right range. So what we do there is we take that 100 feet of piping and we add a safety factor of 50%. What that does is that accounts for any additional losses that would be in the system, like fittings, valves, elbows, tees. All these things induce an extra pressure loss than just a straight pipe. So by adding 50% additional, what we would call straight pipe or linear equivalent pipe, we help to account for those losses. So technically, we're now looking at 150 feet of total piping length. The 30 psi pressure delta P is the pressure loss that we're going to say through the actual process itself. So a heat exchanger that's cooling oil on a hydraulic system, that heat exchanger is going to have a pressure loss associated with it. And so that's something that would be spec'd out from the manufacturer of that piece of equipment. In this, we're arbitrarily going to put 30 psi for the example. So based upon the 1.9 psi loss per 100 feet at 150 feet total equivalent piping, plus the 30 psi loss, we're looking at a total delta P of about 33 psi. So we go over to our graph and we plot that on there. Now we know our design point. So when we're looking at this design point, we then refer to those pump curves that are shown on that graph. And what we're seeing here is that our design point is below that black line, which is a 1.5 horsepower pump. So that means that pump will be capable of meeting the demand of the system based on what we have designed it for. So now we're going to change it a little bit. We still have the same 5-ton chiller. We still have the same piping. We still have the same process. But what we're going to want to try to do is achieve double the flow rate that we were. So instead of 12, we're at 24. We're still in that 1.25 inch piping because we're still below that max. But now we're closer to the max. So that 6.2 psi per 100 feet has increased because have the same cross section of that pipe, but we're pushing more flow through there. So we're going to have additional pressure losses. The similar type of thing when we're talking about the processes pressure loss. So that heat exchanger that's cooling that oil, it was 30 psi, now it's at 42. And what that actually is demonstrating is that flow rate is related to pressure loss by a squared relationship. So that's how we calculate that 42 when we had started with a 30. So then going through the addition of those things, we come up with just over 51 psi of total loss. So now we know our flow rate at 24. We then have our pressure requirement at just about, we'll say 52, and then we have our design point. So now what we're seeing here is there's actually 3 curves on this graph that won't be able to meet that because the design point is above those curves. So we need to move up to that next one. So that red dashed and dotted line there, the 3 horsepower 2-stage pump. That's how we're going to select that pump to know that that pump will be able to meet our design demand of this double flow requirement. Hope that helps you guys, and thank you for your time.